Hello guys, today we start with the remaining exercise questions of page number 24 of chapter 1 arithmetic sequence. Next question is third question. Question number 3. Prove that the arithmetic sequence with the first term equals 1 by 3 and the common difference 1 by 6 contains all natural numbers. See here, first term we can denote it as f. F is equal to 1 by 3 and d is equal to 1 by 6. Now we can write xn. Xn is equal to dn plus f minus d. Yesterday we have studied d is equal to common difference, that is 1 by 6n plus f minus d, 1 by 3 minus 1 by 6 equals 1 by 6n plus, see, taking the LCM and simplifying, you will get 1 by 6. You can take 1 by 6 common factor. 1 by 6 into, inside the bracket we will get n plus 1. So, xn is equal to 1 by 6 into n plus 1. Now, what you have to prove? Prove that arithmetic sequence with the first term 1 by 3 and common term 1 by 6 contain all natural numbers. Now, substituting values for n. Xn is equal to 1 by 6 into n plus 1. If you substitute n is equal to 5, you will get 5 plus 1, 6. 6 by 6 is equal to 1. First we are giving n is equal to 5. Now, next number to be given. See, in order to divide by 6, you have to give n is equal to 11. 11 plus 1, 12. 12 by 6 is 2. We get another natural number. Now we have to give n is equal to 17. 17 plus 1, 18. 18 by 6 is 3. So, therefore we can say all natural numbers will occur in this sequence. All natural numbers will occur in this sequence. Okay. Third question over. Now move on to fourth question. Question number 4. Prove that the arithmetic sequence is the first term 1 by 3 and common difference 2 by 3 contains all odd numbers but no even numbers. See what is said in the question. Prove that arithmetic sequence with the first term 1 by 3. First term is, I am not writing the question. First term 1 by 3 and common difference 2 by 3. Now what we have to do? We have to find xn. Xn is equal to dn plus f minus d. Yesterday we have studied. Equals d is equal to 2 by 3 n plus 1 by 3 minus 2 by 3 equals 2 by 3 n plus 1 minus 2 minus 1 by 3. This we can write as xn is equal to 2 by 3 n. taking 3 as denominator. 2n minus xn is equal to 2n minus 1 by 3, or we can write this as 1 by 3 taken out 2n minus 1. This is the xn of the sequence. Where see here 2n minus 1. This is the general form of odd numbers. Therefore, value of 2n minus 1 is always odd. To get the even numbers must be 2n. Here 2n minus 1 is always an odd number. There is no even number. You can write value of 2n minus 1. That's the general form of, that is algebraic form of odd numbers is 2n minus 1. We have studied earlier. 2n minus 1 is always odd. Therefore, no even number occur. Therefore, in this sequence, there is no even number. This is the question. No even number. Okay. Fourth question over. Now, fifth question. What is the fifth question? Prove that the sequence of all the terms of the arithmetic sequence 4, 7, 10 dash dash belong to the sequence. Prove that, read the question one more. Prove that the sequence of all the terms of arithmetic sequence 4, 7, 10 belong to the sequence. Now, here first term is 4. We know the common difference is equal to 7 minus 4 is equal to 3. Now we have to find, what we have to find? We have to find xn. Xn is equal to dn plus f minus d. Dn plus f minus d. See, d is equal to 3. So we can write equal to 3n. Xn is equal to 3n plus 4 minus 3. What you will get? We will get 4 minus 3. 4 minus 3 is 1. We will get xn is equal to 3n plus 1. See here it is 3n plus 1. Now we have to, what is to be proved? Prove that the squares, you have to find the square of this sequence. Square. Square is equal to 3n plus 1 the whole square. We can expand using the identity. What is 3n plus 1 the whole square? 3n plus 1 the whole square is equal to a plus b whole square form. A square plus b, 2ab plus b square is equal to 9n square plus 6n plus what? Equals. We can take 3 common factor from these two. 3n. No need of taking n, 3 only. 3n square plus 2n plus 1. 3n square plus 2n, it is in bracket, plus 1. We can assume this as k. We are giving the value 3n square plus 2n is equal to k. So this will be equal to 3k plus 1. 3k plus 1. See, divide this by 3. We get 1 as the remainder. 1 as the remainder. So, what is the question here? Prove that the squares of all the terms of the arithmetic sequence belong to the sequence. Squares. All the we get 1 as the remainder. So, what to write? When we divide, so we can say that 3k plus 1. So, the squares of all the terms, all the terms of this series contain this. We will write this is of the form, this is of the form 3k plus 1. Dividing by 3, we get 1 as the remainder. This is of the form 3k plus 1. So, squares of 'of all terms are in this series. Squares of all terms are in this series. Okay, this is the answer of question number 5. Now we move on to 6th question. What is the 6th question? Prove that the arithmetic sequence, question number 6. Prove that the arithmetic sequence 5, 8, 11. 5, 8, 11 dash dash contains no perfect squares. No perfect square. First term is equal to this term. This type of questions we have to find xn. T is equal to 8 minus 5 is equal to 3. Xn is equal to dn plus f minus d equals 3n plus first term 5 minus 3. That is equal to xn is equal to 3n plus 2. See, when we divide a perfect square with 3, see, I will show you the example. Which are the perfect square? 4 is a perfect square, 9 is a perfect square, 16 is a perfect. When you divide a perfect square by 3, 1 3 is 3, remainder 1. 3 3 is 9, remainder 0. 3 5 15, remainder 1. So from this we can understand that if we divide a perfect square with 3, we have to get remainder 1 or 0. Here the remainder, when we divide this by 3, here it goes, here 2 is the remainder. So in order, if we divide any perfect square by 3, we have to get the remainder 1 or 0. Here comes the remainder 2. So we can say that does not contain a perfect square. Here if it was 1, the answer was right. Here you got 2 as the remainder. So we can say that it does not contain any perfect square. We will write when we divide. In the previous question also we have seen, when we divide any perfect square, by 3, we have to get the remainder. We get remainder 0 or 1. Here what we got? 2 as the remainder. Therefore we can say that it does not contain any perfect squares. Here we get remainder 2. On dividing 3n plus 2 by 3. Hence, no perfect squares occur in this series. No perfect squares are in this series. In this series, no perfect squares. Hence, no perfect squares are there in this series. Now, 6th question over. Now, 7th question. Question number 7 is, write the whole numbers in the arithmetic sequence. Question number 7. Whole numbers in the arithmetic sequence 11 by 8, 14 by 8, 17 by 8, dash dash. They form an arithmetic sequence. They form an arithmetic. Write the whole numbers in the arithmetic sequences. This is arithmetic sequence. They form an arithmetic sequence. Whole numbers also contains in this. You have to show that. A is equal to first term. F is equal to 11 by 8. D is equal to 14 by 8 minus 11 by 8 equals 3 by 8. Here we have to find xn. Xn is equal to dn plus f minus d is equal to, what is the 3 by 8 n plus 11 by 8 minus 3 by 8 equals 3 by 8 n plus 11 minus 3, 8 by 8, that is equal to 1. 3 by 8 xn is equal to 3 by 8n plus 1. If n is a multiple of 8, we can give them values and find out the whole numbers. If it is a multiple of 8, have to give n is equal to 8. See, when n is equal to 8, 8 by 8, when n is equal to 8, 3 by 8 into 8 plus 1. So, 3 plus 1, 4. Now, n is a multiple. So, next is 16. 3 by 8 into 16 plus 1. 8 to 3 to 6 plus 1, 7. So, when n is equal to next is 24. 3 by 8 into 24 plus 1. 3 3 is 9 plus 1, 10. So, we get 4, 7, 10, this sequence. They are whole numbers in this sequence. Let me rub it off. So, we can write if n is a multiple of n, if multiple of not n, multiple of 8, if n is a multiple of 8, if n is a multiple of 8, what we can say that then, I have shown you, then 4, 7, 10. On substituting values for n, the multiple of n, 8, 16, 24, like that, we get 4, 7, 10, that type. Is a sequence. Is it an arithmetic sequence? Yes. Is a sequence. Is a sequence with a common difference. With a common difference 3. So, this is an arithmetic sequence. So, this sequence 4, 7, 10. So, this is an arithmetic sequence. Okay, 7th question over. No more questions in this exercise. So I think you all understood this class. Let me wind up. We'll continue the next topic in the next class. Okay.